Okay, sorry about that. So, like I said, I want to talk about oxide heterostructures and some of the work we've been doing. And this wouldn't happen without lots of very good collaborators. I especially want to acknowledge the group of Jack Chakalian. We've worked very closely together for many years now. Actually, I think we just crossed a decade, which is sort of scary. And also a lot of good collaborators at Argonne National Lab, where I'm based. We've been doing some theory with James Rondinelli, particularly in the realm of how strain controls structure of oxide films. My student, Yicheng Teng, who's co-advised with Mike Bedzik at Northwestern, and also with Rosita Pencheva in Munich. Okay, so I have almost no background whatsoever, and for that I apologize. So if there are questions, you can come to me later. Many of the students will be here all week, so I'll be around all week if you have more questions. You know, this is the usual picture we toss about. We've seen already many times of why strongly correlated electron systems are interesting. You get this emergent behavior because of all of these competing things. And now what we want to do is we want to redo this problem in the realm of oxide heterostructures, where we want to look at all these competing interactions. And so, like Andy, I'm making use of this figure from our review article that has yet to appear. And really try to see how this competition emerges across interfaces and what kind of new phenomenon we can see in the realm of oxide heterostructures. And the key is really been on the experimental side is that over the past decade, we've really seen a big growth in the growth of these materials and the advanced characterization so that we can really start to get a much better understanding. And so what we're looking for is we can build these heterostructures of a whole variety of different types, but then we have to understand what happens to these structures. So one important question will be strain. They're always strained. And so what does strain do to the properties, and what does it do to the structure? Also charge transfer. As Andy mentioned, you know, in semiconductors we have this wonderful paradigm to describe all the charge transfer, which doesn't exist in strongly correlated materials. Then, of course, confinement, because now we can take three-dimensional materials, make them as very, very thin layers, and now we have a two-dimensional material. How do things behave? And then, of course, I stuck this in because Andy had it, I think it's a good one, is this proximity of phases. Now we can build together, I'll touch on this case here, which is a cuprate manganite. This is a proximity of superconducting, a high TC superconductor with a ferromagnet, which of course don't like each other. What's going to happen at the interfaces? And I want to touch a lot on how to control orbitals. So orbitals are a degree of freedom. They're probably one of the hardest to experimentally control. And oxide interfaces give us some roots. So here's some theoretical motivation. So why would we want to do this? Well, we could potentially try to build some better superconductors, or not, as Andy might say. But the point is, it's a motivation to try to go after how to build new types of materials. And the key to this is the control of the orbital degree of freedom in an oxide heterostructure. And it started as a very simple model of, well, if we have octahedra, if we strain them in a certain way, if we stretch them, they'll squish out a plane. We can use this to change the crystal field splitting. We can throw in some confinement by making it one layer, and everything is wonderful. But of course, life never turns out to be that easy. And we learned a lot in the course of this, which I'll talk about a little later. So I want to touch on several examples in the class of materials known as nickelates. And this is, and I have a phase diagram in a second that I'll get to. And I want to talk both about strain control of single layer films, where we're really just trying to see how can we control the orbital degree of freedom in a film. And in this case, you're going to see that symmetry really matters. This is going to become one of the design rules that we're going to start to use. And I'll explain what I mean by that. Then we can move to this realm of confinement, where we can start to grow very ultra-thin layers. And we can try to play with confinement plus strain to control properties. Okay, so the first question was strain controlling structures. So being a physicist and not a material scientist, strain to me was very simple. We knew experimentally that often we can measure the lattice parameter. That's very easy to measure. And what we knew often is that if I stretched it, it would squish out a plane. It does this for a simple physical reason. It wants to try to conserve the unit cell volume. So if it squishes out a plane, then I can think of strain in a very simple way. If I'm trying to control orbitals, life becomes very good because I simply have an octahedra that I'm stretching or squishing. And correspondingly, I can move these electronic energy levels around. So sounds great. We start this experimentally, and then the first thing we have to learn is that, well, in the first one I showed you a cubic material. These materials are really not cubic. Very few of them are cubic. They're often rhombohedral, orthorhombic, and this means the bond angles are not 180 degrees. They're often very tilted. And you ask, well, why do I care? You care because if you think of this as a ball and spring kind of problem, it's a lot easier to bend a spring than it is to stretch a spring. So what we've seen now, both theoretically and experimentally, is that often when you strain these films, it wants to bend the bond angles before it stretches the bonds. And this means we have to rethink this whole picture because I'll show you some cases where you can put on a whole lot of strain and you do a whole lot of bond angle bending, but not much bond stretching. And so if I want to try to control those orbitals by stretching the bonds uniaxially, this is going to be a problem, of course. So what we've learned in these materials is that if you think of the oxide, of the octahedra as sort of your functional unit, there are basically three things you want to control in a strongly correlated material. You want to control the size, which typically correlates with the charge. You want to control the shape. This has to do with which specific orbitals are occupied. And you want to control the connectivity. That is how the bond angles are bending, but also the symmetry of how the bond angles are bending. And I'll say more about this in a minute. But the challenge is, from a point of view of strain, we mostly control this. And then these other phenomena sort of follow on as second-order phenomena. So this is the challenge, is we have to build this paradigm of how connectivity changes with strain, and then how does it evolve into these other degrees of freedom that we want to control. Okay. I'm going to say very little about the probes I use other than give you a basic overview. I'm by trade an X-ray spectroscopist. And we use X-ray spectroscopy because it measures a lot of nice things. And you can do this all in the same experiment. So if you remember nothing else about X-ray spectroscopy, the first thing is it's element resolved. So this is really nice. We can look at ultra-thin layers. If we have super lattices with lots of different layers, we can pick out what different layers are doing. And we can measure a variety of different things. We can measure the chemical valence. This is, of course, very important because the properties in these materials change very strongly with charge. We can look at which orbitals are occupied, and I'll show you some examples of that. And we can also look at the magnetic state, because obviously these things coexist, and we want to try to control all of them. I will also say a few words about X-ray diffraction. If you don't know anything about X-ray diffraction, we use it to measure crystal structure, and you do it by bringing an X-ray in and out, and if it correlates, if that in and out correlates with the planes of atoms, you'll see a so-called diffraction peak, and the position of that peak can tell you about lattice spacings and all of these kinds of things. Okay, so let me start with this case of strained nickelate films. Andy already showed this phase diagram. So nickelates, nominally from an ionic point of view, are a D7 system. So they have a fully occupied T2G orbital with one EG electron. Although they're not Jahn-Teller active, which you would expect with one EG electron, and that's a whole talk in itself, which I won't go into. But it's the reason that these materials were interesting, because they have one electron in that EG orbital. So if you can really split those orbitals, it's a good system for this. And if you're over here, if you have lanthanum, it's rhombohedral and metallic and paramagnetic. As you go this direction, in terms of shrinking ionic radius, what happens is you lower the symmetry to orthorhombic, and at the same time, once that happens, you start to have this first-order metal-insulator transition. And that metal-insulator transition coexists with an antiferromagnetic transition at a higher ionic radius, and then as you go smaller, they start to split apart. And I should also point out that the symmetry lowers again here, so it goes from orthorhombic to monoclinic. And in a very, very simple model, which may be right or wrong, I don't want to go into that as well. This was a paper from Igor Mazin and Kamsky and some others from 2007, I think it was, where they talked about this in a very simple picture. So you could talk about the system as charge ordered. That, of course, is a whole other talk in itself. But the basic idea is it could either, as an EG1 system, it can Jahn-Teller distort, and gain by doing that distortion, or it could charge order, and it turns out that nickelates have a very strong propensity for what's called a breathing mode distortion. That is, the octahedra can change size. And you can actually gain a lot of energy through that breathing mode. And so it turns out if the conditions are just right, even though you have to pay a U to put 2 electrons here, if you gain a lot in the breathing mode, then basically you could stabilize this kind of bond disproportionated state. So then the question is, well, if I can use strain to control this distortion of the octahedra, maybe I can play a game between these. Maybe I can use strain to move between one and the other. So the first question is you have to learn about what strain does. So we did an example experiment where we compared lanthanum nickelate, which is rhombohedral, to neodymium nickelate, which is orthorhombic. These have, if you think of this as a pseudo-cubic structure, they have very similar lattice parameters, but obviously they have very different symmetries, and I'll talk a little bit more about this in a second. And so the question is, how do these respond to strain? And the first thing is we want to measure the polarization of the orbitals. So how do we do that? Actually, I forgot to put the picture in before this. The idea is we have a film with the c-axis oriented out of plane. So what I can do is I can put the polarization of the X-ray either out of plane or in plane, and I can probe the differences between those 2 electronic orbitals. And what you find in lanthanum nickelate, even this, though this is under 2% tensile strain, we see no orbital polarization whatsoever. However, if you do the same experiment in neodymium nickelate, which is under a very similar strain state, you see a clear difference between these 2 spectra, showing there is an orbital polarization. It's small, but there is a non-zero orbital polarization. So the big question is, it sounds like this octahedra is still regular. This octahedra is distorted. It's collapsed out of plane. So why the difference between these 2? From a pseudo-cubic perspective, they're very similar. So then we started to think a lot about the symmetry of these films. So for example, and in particular, people talk a lot in terms of what's called Glaser notation. This is a way to basically take regular octahedra and concoct many different space groups by simply having rotations in 3 different directions, and those rotations can either be in phase or out of phase. So for example, in rhombohedral, they're out of phase in all 3 directions, and they're all A, which means they have the same magnitude. Whereas in orthorhombic, they're out of phase in 2 directions, but they're in phase along the c-axis. And so these have a very different rotational symmetry. And we actually measured this in the films, so we can actually go and measure the crystal structure in these films in the synchrotron, and we can show that the rotational patterns, even though you put these under very high tensile strain, they still maintain a memory of the original rotational pattern. So rhombohedral still has this minus, minus, minus. The neodymium nickelate still has this minus, minus, plus. So you say, okay, well, why do I care? Why should I care about this? You care because symmetry is extremely important. It turns out that in a rhombohedral space group, it does not allow a Jahn-Teller distortion. So in order to impose a Jahn-Teller distortion on a rhombohedral material, you have to drastically lower the symmetry. But that, of course, means energy, because you're going to have to pay all of that strain cost to do it. Whereas orthorhombic allows a Jahn-Teller distortion. So what we found was that basically the knowledge of the bulk materials and how symmetries connect to orbital polarization is actually extremely important because it's still very relevant in these films. And so you can use this as now as a design rule. This, I showed you the case of orbitals. You could think of similar design rules for magnetism. And probably we should have known this all along, but of course, sometimes you have to learn things the painful way. And okay, so that was the case of films. Now we can go to heterostructures. And we did the same experiment in heterostructures because the goal was to really use a heterostructure to cause orbital polarization. So now I'm showing you a lanthanum nickelate, lanthanum aluminate heterostructure where I have 1 unit cell of each material. And again, this is this spectroscopy where I'm measuring this nickel L edge. I'm varying the polarization. And I find 2 very strange things. In lanthanum nickelate as a single film, there was no orbital polarization. Now I'm seeing a difference in intensity here. But I'm also seeing that these peak positions are in exactly the same place, which they weren't in the case of neodymium nickelate. They were actually shifted because I was changing the bond length, which changes the energy of those levels. So this is a very strange problem because I have orbital polarization, but it seems like I do not have any change in crystal field. So the question is, how does this occur? It occurs because these materials are highly covalent. So this is another ingredient of nicolates that makes them both interesting and frustrating. So that the material is not really 3D7, it's actually really 3D8 with a hole on oxygen. So then what happens at the interface is a very interesting, at some level, simple chemistry problem. On the one side, I have aluminum. Aluminum is formally ionic. It wants oxygen to be 2-. Over here, I have nickel. Nickel wants holes on oxygen. There's a battle across the interface. And what happens is the aluminum actually pushes some holes off of the apical oxygen and back into the nickel manifold. And so in the end, you generate a orbital polarization through basically interface chemistry. And Andy also wrote a paper about this at about the same time. So So this is an interesting phenomena where you're controlling orbital polarization through basically interface chemistry, not through stretching the bonds. Okay, oops, I was supposed to take this out. Unfortunately, no superconductors. So in the last example of this, I wanted to touch on the question of neodymium nickelate. So I'm going through this very fast, but lanthanum nickelate is about one of the most boring oxides you can find. It's a metal, it's always a metal, it stays a metal, and whereas neodymium nickelate has this first order metal-insulator transition. So now it's interesting to go from a material that's sort of not very active to a material that's active and ask, well, what can we do in a heterostructure with that material? So the first thing we did was actually we studied the dependence of strain on just a single layer. And what we found was, under tensile strain, this material maintains a first-order metal-insulator transition. But as you apply compressive strain, you completely suppress that metal-insulator transition. And you have this very nice crossover through some very interesting regions here. So then the question is, well, if I go from here to here and I completely kill that insulating state, can I bring it back in a heterostructure? And the answer is yes. So what we did then was we made a heterostructure of these materials. So now I'm going to compare two, neodymium nickelate that has basically lanthanum aluminate on either side. You can think of this as like a simple quantum well. Or I can have a single layer of this film. And then one can play with the thickness of this layer to basically isolate out what is interface versus stuff going on in the bulk of the layer. And what we found was when the layers are thin, when the layers are thick, you see like before, it's still metallic. Even here in a quantum well, it's metallic with a very small upturn. But when the layers are thin, I can completely bring back that insulating state. And it turns out that the big difference here is that when I have just a single layer film, I have a lot of orbital polarization. But when I put that thing into a heterostructure, what happens, especially if the layers are thin, that chemical pressure effect that I showed you in the previous example comes into play. And actually, if I'm under compressive strain, these two things are working against each other. So what happens is, in a quantum well, I can take a material like this at a single layer, which has an orbital polarization, and put it into a quantum well, and I can completely kill out that orbital polarization. And it seems like this is very closely connected to whether or not one can bring back this metal-insulator transition. And so this is a very quick look at this class of materials, sort of showing you, and this goes back to this question, am I really doing something as simple as tuning this balance between Jahn-Teller and charge ordering, if this is really the correct picture? But these are all sort of now data points one can sort of put in and start to formulate as a model, because as Andy discussed in his talk, I think some of his models are getting very, very close to really giving us a good representation of the physical properties of the bulk materials. Now if we can take this to the next level and put this into heterostructures, and rather than having some simple sort of cartoonish kind of model, build this into a framework where someone can really understand what is going on. So I don't, how much time do I have left? I don't know.
You have about 15 minutes.
Oh, okay, good. So,
Including questions.
Okay, that's fine. That's perfect, actually. So that was a case where I had a material that started with no orbital polarization, and I was trying to impose orbital polarization. And the outcome of all of those studies, the physics was very, very interesting. We enjoyed it. But one of the general outcomes was the following, that if I have a material that has a very large bandwidth, strain can only impose like sort of 100 millivolt splittings on the system. It's extremely hard to generate large orbital polarization. So the prediction of superconductivity required 100% orbital polarization. In almost all of my experimental evidence, I'm getting something like 5 to 10%. Okay, so it's not going to cut it. So,
do you think this is a general statement, or that other oxides could be better, like the early ones, which have a T2G shell instead of an EG shell?
So in some sense, you're absolutely right. I mean, the question is, what is going to be the optimal material? I don't know. I know that having a big bandwidth like an anicolate is a problem. And
is it useful to push the oxygen to lower energy?
Well, actually, I think what you want to do is you want to go away from perovskite completely.
Okay.
So I think the problem is you have an octahedra. And I think it's very hard to impose super large distortions on the octahedra. So what you want to do is you want to go to a tetrahedra, for example. Because like in a cuprate, which is what I was going to touch on in this example, you get an extremely large orbital polarization, and you get it for a very simple effect. That out of plane, there's no atom there. So it totally changes the crystal field. Whereas in this thing, how far am I going to stretch this? I can only stretch this octahedra so much before it's going to fall apart. So I think the paradigm is actually to go beyond that. So let me talk about it in the context of this example, because here we do absolutely the reverse. We take a material with huge orbital polarization and we kill it. So you could, of course, do the converse. You could take a material that had no orbital polarization. So I think the answer to your question is that, at least my personal feeling is, I think we have to move away from the perovskite. I think going to narrowband perovskites could certainly help. So there can be lots of examples there where one could do that. And, but nicolates are challenging because they're big, large bandwidth, which of course comes back to the fact they're highly covalent. And that's, so the early ones are not as covalent, so that might help you. Okay, that's a long-winded. So another example is to move to a material where I have competing order. So in this case, I have a high temperature superconductor. This wants electrons paired in singlets in proximity to a ferromagnet, which wants things parallel, okay? And in general, the ferromagnetism is going to win because this coupling is like orders of magnitude larger than this coupling. But of course, if I put these things into very close proximity, you know, who knows what's going to happen? And so I'll talk a little bit more about the experimental geometry in a second. And so when we originally did this, so we worked on this, Jack and myself, along with Keimer's group, worked on this back in 2007. We were looking at basically very thick structures. We had very thick layer of superconductor, a very thick layer of ferromagnet, and we stuck them together. And we had some creative ways where we could try to tease out the electronic properties at the interface. And what we found was that if you measure the bulk of the cuprate, and I come in at a geometry like this, I have polarization either out of plane or in plane, what you have is an extremely large orbital polarization. This happens for a very simple reason. The cuprate has one hole in the D band, and because of this broken, strongly broken symmetry of a very long bond here and much shorter bonds in plane, that hole sits in a planar orbital. And so the out-of-plane orbital is completely filled, so I see a very weak absorption there, and the in-plane orbital is completely empty, so I see a very strong absorption there. But then the question is, what happens at the interface? Now at the interface, I have a manganese coupled via this oxygen to this cuprate, to this copper-oxygen plane, where all of this action is occurring. And what we found was, if you can go to sort of an interface-sensitive mode, that basically the orbital polarization was largely killed out. We seem to have some level of occupancy in both layers. And there was a shift as well, which was sort of indicating some level of charge transfer between the materials. And actually, I don't know if I have the picture. And the simple model was the following, that I have a copper-oxygen plane, it's coupled to this apical oxygen. Now, normally in the cuprate, this apical oxygen is connected to nothing else. But now I've connected it to a manganese. So I basically made it sort of a three-dimensional entity. And depending on what's going on in this manganese, I can basically hybridize with this copper. And depending on the details of where the D states align in the two layers, you can basically cause this kind of state where you basically mix up the two orbitals. But when we did this, we were looking at very, very thick structures. And so lately, we've been going back and revisiting this problem because the problem was we knew there was something going on at the interface, but we really didn't know how far. How far does this penetrate in the layer? Is this a very abrupt phenomena? Does it continue for many layers? And also, where is the superconductivity? We knew if we had a thick layer, even though we saw this phenomena at the interface, the layer still in the middle was superconducting. And so the question is, where do these crossovers happen? So this led us to doing some very detailed structural studies of the interface. So first, we basically did cross-sectional TEM, which allows us to look at where the atoms are. This was done with Dave Muller's group. And this allows us to really look at what is the interface chemical structure in this material. And so what you can see is there's a very sharp divide. You basically have this manganese layer. Actually, which ones are the manganese are the red. Then I have a barium oxide layer, and then I go into this copper oxygen double plane. So this is sort of a schematic picture here on the side. So we know really what this chemical structure looks like. It's very sharp, and this is one of the nice reasons for this system is that you can create these heterostructures and then study the details. But the question is, this can tell you sort of where the atoms are. But the question is, well, what's the action going on in the bands near the Fermi surface? Because that's what, superconductivity and things like that are going to be tied to those details. And so what we did was we actually developed a whole approach. So Taeyu Chen, who was a former postdoc, to do cross-sectional STM. So this is something that had been done for years in semiconductors. People would crack things on the side. They could look at PN junctions and how charge occurred. But it had never been done in the oxides. So we actually, over the course of several years, developed this in oxides. And we're able to basically map across an interface. Now, what am I showing you here? What I'm showing you is a compilation of, this is a spatial distance. And you can see it here, positioned in sort of nanometers across this interface. In this direction, I'm showing you the basically bias. So this is the bias I apply to the tip. So basically, you can think of this 0 as the Fermi level. Sorry, my thing fell apart. This is the Fermi level. This is the valence band in the cuprate. This is the conduction band in the cuprate. And so you can measure this. This is one of the nice things you can do with STM. You can do these spatially resolved density of states. And you can measure this across the interface. And what did we find? Well, what we found was that electronically, this interface is extremely sharp. So we came up with a width of 0.5 nanometers. It's literally like an extremely sharp interface. The other nice thing is we can see that, for example, the band alignment. Like I mentioned, we have no model for these kinds of systems. Now, using this kind of approach, we can actually measure the band alignments. So in this case, the conduction bands were aligned. Here's the Fermi level. I have the valence band of the cuprate here, the valence band of the manganites a little further down here. It's not shown on the structure. And so what we found was this interface is actually extremely sharp. And I didn't think I would have time to go into it. We've actually been doing spectroscopy in ultra-thin structures. And this is very consistent with the fact that this phenomena that I showed you here, this interfacial orbital reconstruction, our recent data on very thin structures shows that this is really limited to that first copper-oxygen plane. And the next copper-oxygen plane looks very much like the bulk. And this is consistent with this idea that the interface is extremely electronically sharp. And so this gives us a very nice system to look at. Unfortunately, this system was not capable of running low temperature STM, so we weren't able to do that experiment to look for the superconducting gap, but I think those are kinds of things we'd like to do in the future. Okay, and then the last two slides I have actually tie in very nice with Philip's talk, which is all of these properties I told you were static properties. I think, as Philip said, really, the dynamical realm is very exciting, looking for non-equilibrium phenomena in these materials and trying to see what will appear. And so let me give you just two highlights. So one is the idea of what you can do optically in a film with light. So I'm showing you here an experiment where we're doing an X-ray diffraction measurement, time resolved, after we've pumped the material with laser light. And this was bismuth ferrite, which is a multiferroic material. And what we found was actually you can induce ultra-fast strains in these materials. And in a film, this is very interesting because what you can do is the film can't move sideways because it's clamped to that substrate. So it can only move in the out-of-plane direction. And so what we found is we could generate an ultra-fast lattice expansion. And this is almost like you're tying a string to this material and pulling on it. And so here I'm showing you what the lattice structure is doing. It turned out with bismuth ferrite, the electronic properties didn't really change much. But in a material that was very sensitive to the lattice expansion, you could do a dynamical experiment where you could try to drive it in sort of new ways and see what would emerge. But the challenge also with optical pumping is that you put in a whole lot of power with this laser light. And so you do a whole lot of heating, which of course you don't want. And that's a challenge because if you think of it from an energy point of view, it means only a tiny fraction of energy is going into exciting the mode you want, and all the rest is just heating it. So that's why the idea of mode-selected pumping is very interesting. So the idea, if you could come in and say pump a phonon, or pump across a gap, excitons, polarions, you can pick whatever you're favorite. This could be a very interesting modality for trying to control materials in sort of new ways. And I think Andrea Cavallari's work has sort of shown us some real interesting possibilities for that. You can also, something we're working on now is using broadband terahertz, which you can think of as like an ultra-fast electric field. So this means you can actually pump the system with sort of a 300 femtosecond electric field. And these electric fields can be made quite large, especially if you use sort of what's called nanoplasmatic resonators to focus the energy of that light. So then you can do ultra-fast electric field experiments because you want to see what happens to these correlated electrons as you apply very large electric fields. Can we generate phase transitions? There's been some very interesting results using this idea from Rick Averett at Boston University in VO2, generating phase transitions. Can you really generate a phase? And then the next question is, how does it work? You know, I mean, I think we have no idea, and that's an exciting opportunity for materials. Okay, and so with that, I will finish, and thank you very much.
I have time for a few quick questions.
Can I ask a question? Yeah, so by shining these photons when you were changing the structure,
Yes.
that changes should be a local structural changes because your spot size is.
Yes, it occurs within the laser spot. And actually the mechanism in bismuth ferrite is what happens is it's not a thermal mechanism. We're able to figure that out. That you excite a carrier high in the conduction band, it quickly relaxes down to the bottom of the conduction band. But
No.
because of the band structure of bismuth ferrite, it can relax back to the conduction band, but it's a slow process. And so what effectively you do, and this is sort of a similar mechanism in VO2, is when you populate the conduction band, you soften the bonds. And so then the bonds soften some, and the lattice expands. So a similar thing happens in VO2.
But that would be a very local effect.
Yeah, it's wherever you're shining light.
Yeah. So the properties you are measuring, that's a global property you are measuring.
Oh no, actually the X-ray spot is smaller than the laser spot.
I see.
So yeah, that was something we had to do. We had to make sure that the illuminated region was larger than the region we were probing.
Okay.
Maybe it's more to do with not the lateral dimension, but the depth into which you're probing, because your laser, I don't know in how deep into the system it's exciting, where your X-rays penetration depth could be different.
This is why films are great.
Okay.
Because the film was 35 nanometers. The extinction depth of the light was 30 nanometers.
Okay, so
So
that's
it was
wonderfully
really like,
matched.
it was like well matched to the
That's
film.
wonderfully
And then
matched.
because we're measuring just the film,
Okay.
it allows, you're right. If we've tried similar experiments in bulk materials, and those are very hard.
Exactly, that's what I
Because
had in
you're
mind.
probing mostly the bulk
Exactly.
that's doing nothing.
Because the lateral
And so-
matching is easy, but the depth. Just a quick comment on the early part that you pointed out, that interface, the stretching and the contraction and expecting the volume to conserve by changing the bond length in the perpendicular direction doesn't happen quite. But this concept of chemical pressure by putting a larger or a smaller
Yes.
substituting atom, and you can see that the unit cell is changing in X-ray diffraction very systematically, which is the basis of
so-
chemical pressure.
yeah.
It turns out that actually even in that case, the bond lengths are not changing at all. It's actually what is changing is the angle. So this tracking of, this is a
yes.
mismatch between the way we probe with X-ray, which is looking at the long length scale of the structure, and at the short length scale, at the microscopic length scale of the bond lengths, they don't change at all. So the change that you see over a long length scale is actually adjusted by the angle change, which you don't appreciate often, actually.
Yes, yes.
So that's something
And
that
which
we-
is also why it's important to study bulk materials as well as film
Exactly,
materials.
exactly.
Because then you can learn from both.
A related question. I think it has been under static pressure, hydrostatic pressure.
Yes.
Often bond angle doesn't change, but bond length indeed shrinks. But in
It
perovskite,
depends. Yeah,
but
it
you
depends.
said-
It depends a lot on the system.
Yeah.
So you're absolutely right. There's been a lot of work, and it turns out one of the extremely important parameters, which I think will play out in films as well. In the bulk, they look at the compressibility. So if you have an A site, it has 12 oxygens. So you can look at the compressibility of the A site versus the compressibility of the B site. And depending on what those compressibilities are, in one case, you'll get compression of the octahedra without much change in bond angle. In the other case, you get changes in bond angle without much compression of the octahedra.
So if you choose a system, you can
Yeah.
shrink
Yeah.
the bond length in
Yeah.
thin
Yes, and you're right. And maybe we can use those bulk studies as a guide for which ones could be good.
Thank you.
That's a good comment.
Any other questions?
Yeah, I have a question about the cuprate. When you do this perverse thing of undoing the orbital polarization somehow,
Yes.
I didn't completely get what happens with superconductivity. Do you actually harm superconductivity?
I don't think that, I have no direct experimental proof, but my belief, that interfacial layer also has magnetism because it becomes coupled to this ferromagnet below. And so the ferromagnet causes a canting of spins. And so I believe you really have something as probably more like an antiferromagnet that gets coupled to this ferromagnet below, which we have evidence. So I don't think there's any superconductivity in that layer. But unfortunately, we don't have any direct proof to show that's the case.
Right. If there are no more questions, let's thank all the speakers in the session and then have lunch.